Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus 2. In this video we're going to be looking at Newton's Polyseries, very famous formula for an extension of the binomial theorem, and the connection with the Harriot-Pascal array. So here is Newton's famous binomial series, starting with a rational number r. It's an expression for 1 plus alpha to the r. This is the usual way it's expressed. And the series is 1 plus r alpha plus r times r minus 1 over 2 factorial alpha squared plus r times r minus 1 times r minus 2 over 3 factorial alpha cubed, and so on. It's an on sequence that keeps on going. Now, the usual interpretation of this in modern analysis courses is that this is expressing a function. We have a function of a real number on the right-hand side involving necessarily, things like 1 plus pi to the 1/7 power or something like that, that we can't actually compute infinite decimals and keep on going. And here this is also in the context of some kind of arithmetic where we're doing this sum with actual numbers, and we're taking this infinite sum and getting also some infinite decimal typically. But we're not able to make that interpretation because we don't want to consider numbers other than rational numbers, and because we want to stick within a context of finite high school arithmetic. So we're going to have to think very carefully about what the meaning of this identity actually is. Okay, so an important special case and sort of motivating example for this thing is the binomial theorem itself. When r is equal to a natural number n, then, well, the left-hand side actually does make sense. It's just a poly number 1 plus alpha to the n. And then on the right-hand side, we get the usual binomial expansion, which we can write as summation k equals 0 to n choose k, alpha to the k. So for example, if we replace r with n, then this term n times n minus 1 times n minus 2 over 3 factorial is just n choose 3, so it's a standard binomial coefficient. So today we're going to be talking about this series and trying to position it in a way that doesn't require any kind of infinite things. And this is part of a bigger challenge, right, to create a kind of a framework for doing polyseries arithmetic more generally. But whatever kind of framework that we do end up agreeing on, these series here of Newton have to be playing a central role. Now, it's useful to have a look at some special cases where we connect with some formulas that we've already found in a previous lecture. So for example, when r is equal to 1/2, we get the formula that 1 plus alpha to the half equals, 1 plus a half alpha minus 1/8 alpha squared, and so on. These are our first 8 terms. And this turns out just to be what we get when we take the Newton formula and replace r with a half. So there's a half. There's a half times a half minus 1 over 2 factorial. There's a half times a half minus 1 times a half minus 2 over 3 factorial, and so on. So this is a kind of a nice way of remembering where these coefficients come from. Similarly, when r is equal to 1/3, then we get 1 plus alpha to the 1/3 equals then this series here. And that's just writing out the Newton series when r is equal to 1/3. r times r minus 1 over 2 factorial, r times r minus 1 times r minus 2 over 3 factorial, and so on. Some other interesting values are when r is a negative integer. For example, if r is equal to -1, then the series that we get is 1 plus alpha to the -1 equals 1 minus alpha plus alpha squared minus alpha cubed, and so on. That's a basic kind of geometric series, and this is some kind of representation of the sum of an infinite geometric series, everything in quotes. If r is equal to -2, then we get an expansion for 1 plus alpha to the -2 as 1 minus 2 alpha plus 3 alpha squared minus 4 alpha cubed, and so on. If r equals -3, then we get 1 plus alpha to the -3, which is then 1 minus 3 alpha plus 6 alpha squared minus 10 alpha cubed plus 15 alpha to the 4th, etc. So for example, this thing here would be -3 times -4 divided by 2 factorial. That's where you get the 6. Okay, so these are interesting kind of special cases, but a major question is how do we derive Newton's series, first of all, and how do we interpret what it's actually meaning? We're going to go back to essentially Newton's way of thinking. Newton liked to write down lots of formulas and then look at tables of things and see patterns. And his approach was of interpolating. So he would try to see some kind of polynomial patterns and then interpolate. And that connects with what we were doing in our first algebraic calculus course in the section on discrete calculus. So to understand how we could generate Newton's series, where it comes from, a great place to look at is the Harriot-Pascal binomial array that we've already seen several times in the Algebraic Calculus 1 course. We saw it first of all in the context of the Pascal array, where we were mostly looking at the binomial expansions. So this is really just Pascal's table, as it's usually called. The expansion of, say, a plus b to the fourth. Coefficients are appearing along this row. But then later on, we saw the same table appear in a different context, in the context of Harriot's kind of difference tables. And we called it H there. And we're going to stick with H because actually Thomas Harriot, first of all, he doesn't get as much credit as he deserves. And secondly, he actually lived before Pascal. He died around the same time that Pascal was born. With Harriot's approach, it's the columns of this array which are essentially more interesting. And these columns, well, we gave them names. We called this one H0, just constant 1. And then H1, just the numbers themselves. And then H2, the triangular numbers. H3, the pyramidal numbers, and so on. And we saw that the entire array could be given by a nice formula. So if the row is, say, n, starting with 0, and the columns are indexed by k, starting also from 0, then the nk element in this array is just the binomial coefficient n choose k. And that, of course, in terms of factorials is n factorial divided by k factorial times n minus k factorial. And it's important to recognize that we could rewrite this by essentially canceling this n minus k factorial with the part of n factorial up to n minus k. When we do that, what's left on the numerator is n times n minus 1 down to n minus k plus 1. And we still have the k factorial in the denominator. And now this product up here is a product of k things, starting with n, but going down, falling each time by 1. N times n minus 1 times n minus 2 down to n minus k plus 1. Altogether k terms. And it's very convenient to use Donald Knuth's falling power notation to express this numerator. N to the k falling. Okay, that's exactly what that is there. Divided by k factorial. So this then is an alternate way of expressing what the nkth element of this array is. Now let's have a look at these entries from the point of view first of the rows and then of the columns. So if we're looking at the rows, then we would choose an n, that's a row position. And then we get a row whose values are indexed by k. So we get so the function Pn of k, which is n to the k falling over k factorial. Here it is again. Now, but as a function of k, this is neither a polynomial nor a rational expression in k. The dependence on k as you go across the rows is difficult. Okay, it's a little bit subtle. There's a k factorial in the denominator, and the numerator here has k terms, and those terms themselves have some dependence on k. So it's a kind of a complicated thing, and in particular, it's not easy to interpolate values. If you want to sort of interpolate this for intermediate values of k, it's not so easy at all how to do that. However, when we look at the columns of h, so now we're fixing a column index, say k, and then looking down the column where the index now is n. So we get, say, h sub k of n. It's, of course, the same expression. But now we're thinking of it as a function of n instead, and we see that it's much nicer. As a function of n, this is a polynomial expression in n. If k is fixed, okay, then it's just a polynomial of degree k in n. And that's great because this then extends to rational values, because you can replace the n and you're going to get column values which interpolate or maybe even extrapolate the given values for currently n, a natural number. So you will be able to extend the columns. We can't extend the rows or interpolate the rows so easily, but we can extend and interpolate the columns. And that's essentially Newton's insight, although he did it maybe in a less direct fashion here, right? It's actually kind of just obvious by looking at this Harriot-Pascal array. Okay, so if we're thinking about extending these columns from natural number values n to rational values r, then it's perhaps interesting to graph them to see what they look like as polynomials. So we're looking at h sub k of r, where k is 0, that's the first column, and then 1, it's the second column, then 2, next column, etc. And here are the actual values, just as polynomials in r, so we're just repeating what we've already done, but expressing it in terms of r. So h0 of r is 1, h1 of r is r, h0, there's its graph, h1 is r, that's just that function there, our variable here in the horizontal direction is r. h2 of r is 1/2 r times r minus 1. So that's a quadratic function that has zeros at 0 and at 1. There it is right there. There's a graph of it. It's a parabola. h3 of r, well, it's a cubic which has zeros at 0, 1, and 2. Where is that? That's the black one here. So it's coming up here through 0, then through 0, and then through 0, and then it goes up in the cubic way. And then the next one, h sub 4, well, it'll be the same kind of thing. It will be a polynomial, a quartic, going through 0, here, 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 and here. And it's that green one. No, it's the red one. Sorry, the red one. There, like this. That's h sub 4. And then the fifth one, this green one, 1, 2, 3, 4 zeros on all of those, and then it goes up. So, for example, if we're, say, looking at the values, say, at 3, okay? The value of h0 at 3 is 1. The value of h1 at 3 is 3. The value of h2, well, that's this quadratic one, that's also 3. The value of h4 is 1. So we get values 1, 3, 3, 1. If we look at the values at 4, h0 will have a value of 1, h1 will have a value of 4, h2, which is parabola, will have a value of 6. h3, which is the black one, has a value of 4 again. And then h4 has a value of 1. So we get 1, 4, 6, 4, 1. Okay. Those are the discrete values that appear along the rows. But now we can adjust this thing, not just for natural number values of n, but for rational values of r. So, for example, if we were interested perhaps in, instead of having maybe something over here, maybe 3 and a third, okay, 3 and a third, then we would look here and just see what the various values of these things were. But crucially, we are not going to get then a finite sequence that ends up being 0, and then after that it's constantly 0. We get something that gives us coefficients that keep on going. Okay? So for a general rational number, we now have an on sequence. Okay, and here's sort of our notation for an on sequence, a sequence, h0 of r, h1 of r, h2 of r, etc. And it's given very explicitly. And then these are going to be the coefficients that are forming the Polyseries. But for a general R, this is not a finite series. It's not a poly number. It's a Polyseries that keeps on going. Okay, so following Newton's thinking, we are now in a position of having this Polyseries or a power series that depends on R. And so now we can kind of give it a name. And the way we're going to do it is we're going to think of this as the object. The object is this Polyseries, which is at this stage still undefined. We haven't defined what exactly a Polyseries is, except to say at this stage rather informally that it's like a poly number that keeps on going. Okay, and that's inadequate, but we are going to move towards trying to clarify what that means. But anyway, so here's a Poly number that keeps on going. It's summation k equals 0, and then it keeps on going. That's denoted by the plus. So the plus means that you keep on adding 1. And here are the terms depending on k. H sub k of r times alpha to the k. Right? So we're getting powers of alpha, increasing powers of alpha with certain coefficients that depend on k and this given r that we're taking. That's just a rational number. So this is the object that we're interested in. This is some kind of extension of a Poly number into some ongoing sense. And we want to give this thing a name, okay, so that we can refer to it easily. We can do arithmetic with it. And here's the name that we're going to give it. 1 plus alpha to the r. But what's here is not a Poly number. It's something else because there's a bracket here on the right, which is pointy. So it's an ordinary bracket on the left, pointy bracket on the right, 1 plus alpha inside, and we're putting an exponent to the r. So I'm doing this because I do not want us to confuse this with the usual expression 1 plus alpha to the r. Okay? I do not want us to think that we're taking an rth power of something here. What we're doing is we're expressing this thing here by giving a symbol. We're creating this symbol. This is just an expression that we've agreed to write down, which will represent this Poly series. And here is the Poly series sort of written out longhand so we can see what the pattern is. Okay, but the 3 dots is really just expressed by this h sub k of r. Now, if r does equal a natural number n, then this expression is actually a finite Poly number, and it's the Poly number that as a Poly number is 1 plus alpha to the n. So in that case, 1 plus alpha pointy bracket to the n equals 1 plus alpha to the n. That's a Poly number. But now what we have is we've sort of cooked up, we've extended our understanding so that we are going beyond just Poly numbers and considering these kinds of expressions for arbitrary rational numbers as well. Okay, so now we come to the main sort of formula that puts this whole story on the map. Like, why are these things interesting? It's because of this theorem, which we'll call Newton's Polyseries theorem. Now, Newton actually didn't really prove very much in this context. He wrote down these formulas. He made some observations, made some tables, saw some patterns, wrote down some formulas, and made some claims. We are going to want to be very precise about this, but at this stage it's still in quotes. So here is the theorem. It's that for 2 rational numbers r and s, if we take the Poly series 1 plus alpha to the r, which we've just defined, and we take a second one, 1 plus alpha to the s, then the product of these Poly series is equal to this Poly series, 1 plus alpha to the r plus s. So we are going to have to interpret this identity. So there's some kind of arithmetic with Poly series which we're invoking here, and then we want to sort of see why it's true. But it's not because of an identity involving powers of real numbers. Okay, this is not like the index laws for real numbers. It's not that at all. We're talking about an expression in the world of the arithmetic of Poly series which we have to bring into focus, and then we have to prove it. And it'll turn out that, well, the crucial identity has been known for a long time, okay? It's the Chu-Vandermonde identity, which goes back many hundreds of years to Chinese mathematician Chu. And another way of saying it, we might refer to the falling binomial theorem, which I think is nice to pin down as a kind of an alternative or a variant of the usual binomial theorem. It's also pretty interesting. So we're going to be looking at that next time. Okay, so looming ahead of us is a great challenge, very important, which I call the Poly series challenge. And it's going to be motivating a lot of our thinking here. What we're aiming towards is to define a precise class or type of Poly series. So we really want to have accurate framework here, in which we can do a consistent arithmetic and which includes the Newton's series that we've just been talking about, along with, well, many other series which are commonly used in calculus. So we want to have a framework for arithmetic which includes the main sort of power series that are usually used, but has a consistent arithmetic in a very well-defined context. Okay? So we're not interested in saying, well, we're considering summations from k equals 0 to infinity of a sub k, a alpha to the k, because we're required to specify things finitely. Okay? Now, there's at least two kinds of approaches that we could kind of aim towards in this context, say of the binomial series. So one is through a formula. So we could say, all right, we're looking for something like this is the expression for the Newton binomial polyseries that we already have. Here is an expression of a polyseries where the coefficients are given by a very explicit formula. Okay, so that's kind of nice. So we have something very finite. This is then a finite kind of thing because we have a finite formula for the kth coefficient. Another approach is to consider this thing in this general form here with coefficient a sub k times alpha to the k, where the a sub k's are defined not necessarily by a formula, but by a recursive relation. In this case, that a sub 0 is 1, and that the k plus first coefficient can be expressed in terms of the kth coefficient by this recursive formula. We take a sub k, we multiply by r minus k divided by k plus 1. Why is that? Well, I remind you that if you want to go from this kth coefficient to the next one, the k plus first, then the numerator becomes r to the k plus 1 falling. That means there's an additional term. We start r minus 1 down to r minus k plus 1. The next one will have an additional term of r minus k. And the denominator, instead of having a k factorial, there will be a k plus 1 factorial. So there's an extra k plus 1 in the denominator. So this is the factor that allows us to go from the kth coefficient to the k plus first coefficient. So that connects with the world of recursion, like computer scientists, a recursive way of conjuring up these coefficients depending on previous coefficients that have been created. In this case, just the previous one, but we could consider more complicated recursions. So our challenge is going to perhaps involve this kind of approach in the direction of formulas, or maybe involving some kind of recursions. But in either case, we want to specify a framework so we know exactly what kinds of objects we're dealing with, okay? That we're dealing with coefficients of the following kind or recursions of the following kind. And the trick is, or the big challenge is, to set this up so that the arithmetic is not just a one-off. So we can do this easily enough if we're just interested in the Newton binomial polyseries. But we don't want to just have one-off definitions. We want our class of things to be closed under arithmetic. In other words, the sum of two such things should be also included. And crucially, the product of two such things should also be included. And if we want to do quotients, well, then the quotient should be also in the framework if it's defined. That makes things a lot more challenging to try to find some framework which is closed under the various arithmetical operations that we might want to have, like the ones that we were talking about in our previous video. So it's a big challenge, and there's a lot to learn. I'm Norman Wahlberger. Thanks for listening.